For AC motors, there is two types, which is induction motor and synchronous motor. Inside an AC motor are housed stationary electromagnetic coils or stators positioned around a movable magnet called a rotor. This illustration of a two-phase motor has a pair of stators connected to one sinusoidal AC input referred to as a phase 1, and a pair of stators connected to a second sinusoidal AC input referred to as phase 2. The two sinusoidal waves are 90 degrees out of phase. This phase discrepancy is the key to creating rotation of the rotor. Let's follow the amount of current applied to the phase 1 and phase 2 stators at various time intervals along with their respective sine waves. The 90-degree offset between the two sine waves causes the polarity of the stators to change in a coordinated fashion to smoothly turn the magnetic rotor. At time 0, phase 1 produces maximum vertical magnetic flux, and the rotor aligns itself vertically with the stator poles. Because phase 2 provides no current flow to the stators, there is no horizontal pole on the rotor. At time 1, phase 1 and phase 2 have equal amounts of current flow, which creates a flux between the adjacent poles. This flux causes the rotor to turn 45 degrees to the left. At time 2, phase 1 reaches zero current flow while phase 2 reaches maximum current flow. This causes the rotor to turn 45 degrees counterclockwise to align itself with the horizontal poles. At time 3, phase 2 has diminished current flow while current flow through the vertical rotor coils increases and reverses direction. This causes the rotor to move another 45 degrees to the left. As the two sine waves continue to induce current 90 degrees out of phase, the rotor will spin and the motor will run effectively transforming electrical into mechanical energy. Induction motors are the most common type of AC motors used in a daily life processes, and their output rotation speed is proportional to the applied frequency of alternate current. Used in almost every process, induction motors are mainly used in water pumps, kitchen appliances, fans, and air conditioners, automobiles, and common industrial machinery like boiler pumps and compressors. AC induction motors are efficient and flexible, which allows them to match the load demand for almost any type of electrical application. By changing the supply voltage of the motor, changing the stator pole number of the motor, changing the frequency of the supply side of the motor.
Alright, for DC motors we have three categories, which is the first one is the brushed DC motor, the second one is the brushless DC motor, BLDC, which we are going to discuss today, and the third one is the stepper SDP. Also under the BLDC we have two types, which is the first one is the outrunner type and the inrunner type, which is both are available in the market. In order to make the operation more reliable, more efficient, and less noisy, the recent trend has been to use brushless DC motors, also known as BLDC. They are also lighter compared to brush motors, with the same power output. The brushes in conventional DC motors wear out over time and may cause sparkling. Thus, the brushed DC motors should never be used for operations that demand long life and reliability. So now, let us see how a brushless DC motor works. The rotor of a BLDC motor is a permanent magnet. The stator has a coil arrangement as shown in the video. By applying DC power to the coil energizes and becomes an electromagnet. The operation of a BLDC is based on the simple force interaction between the permanent magnet and the electromagnet. When the rotor is in this position, along with the first coil which pulls the rotor, you can energize the coil behind it in such a way that it will push the rotor. For this instant, a same polarity current is passed through the second coil. The combined effect produces more torque and power output from the motor. You can see this visualized in the video. The combined force also makes sure that the BLDC has a beautiful constant torque nature. With this configuration, two coils need to be energized separately, but by making a small modification to the stator coil, we can simplify this process. Just connect one free end of the coils together. When the power is applied between coils A and B, let's note that the current flows through the coil. It's just like the separately energized state. That's how a BLDC works. Brushless motors fulfill many functions originally performed by brushed DC motors, but cost and control complexity prevents brushless motors from replacing brush motors completely in the lowest cost areas. Nevertheless, brushless motors have come to dominate many applications, particularly devices. And also they can be found in cordless power tools where the increased efficiency of the motor leads to longer periods of use before the battery needs to be charged. Let us see the application of the BLDC. In transportation, brushless motors are found in electric vehicles, hybrid vehicles, and personal transporters. Most electric bicycles are brushless motors. They are using brushless motors that are sometimes built into the wheel hub itself, with the stator fixed solidly to the axle and the magnets attached to and rotating with the wheel. Most electrically powered RC models are brushless motors because of the high efficiency. In cordless tools, brushless motors are found in many modern cordless tools, notably weed whackers, leaf blowers, and some cordless drill or drivers. In industrial engineering, the application of brushless DC motors within industrial engineering primarily focus on manufacturing, engineering, or industrial automation design. In manufacturing, brushless motors are primarily used for motion control, positioning, or actuation system. Brushless motors are ideally suited for manufacturing applications because of their high power density, good speed torque characteristics, high efficiency, wide speed ranges, and low maintenance. The most common uses of brushless DC motors in industrial engineering are linear motors, servo motors, actuators for industrial robots, extruded drive motors, and feed drives for CNC machine tools. In a BLDC, we use an electronic controller for this purpose. A sensor determines the position of the rotor, and based on this information, the controller decides which coils to energize. Most often, a Hall effect sensor is used for this purpose. The BLDC design we have discussed so far is known as the outrunner type. By using Hall effect sensors as the control, it can provide absolute position sensing. This results in more wires and higher costs. Therefore, another method can be used, which is by using sensorless BLDC control. This can eliminate the need for Hall effect sensors using the back EMF, which is electromotive force, of the motor instead to estimate the rotor position. Sensorless control is essential for low-cost variable speed applications such as fans and pumps. Refrigerator and air conditioner compressors also require sensorless control when using BLDC motors.
AC motors are highly flexible compared to brushless DC motors in many features, including speed control (VSD), which stands for variable speed drive, and have a much larger install base compared to DC motors. The current trend for VSD is to add more features and programmable logic control functionality, which are advantageous for the experienced use, but require greater technical expertise during maintenance. The advantages of using brushless DC motors are it has a long lifespan, little maintenance, and high efficiency, around 85 to 90%, whereas the disadvantages are higher initial costs and more complicated controllers. These type of motors are generally used in speed and positional control with applications such as fans, pumps, and compressors, where reliability and ruggedness are required. For brushless DC motor, the speed or torque characteristic is flat in nature. It enables operation at all speed with rated load, while for AC motor, the speed or torque characteristic is non-linear in nature, and it enables lower torque at lower speed. For brushless DC motor, the output power is high because it has permanent magnets on the rotor. The smallest size can be achieved for a given output power, while for AC motor, the output power is moderate because both stator and rotor have winding. Output power to size is lower than brushless DC motor. For brushless DC motor, the rotor inertia is low. This enables better dynamic characteristic, while for AC motor, the rotor inertia is high. This enables poorer dynamic characteristic. For brushless DC motor, the starting current is rated. No special starter circuit is required. For AC motor, the starting circuit is approximately up to 7 times of rated. Starter circuit rating should be carefully selected. It normally uses a star delta starter. For brushless DC motor, a controller always required to keep the motor running. The controller can be used for variable speed control, while for AC motor, no controller is required for fixed speed. A controller is required only if variable speed is desired. For brushless DC motor, no shift is experienced between stator and rotor frequencies. The rotor runs at a lower frequency than the starter, but shift frequency and shift increases with load on the motor.